video, we'll be doing one example of a percent yield problem. The formula for percent yield is going to be our experimental yield divided by our theoretical yield multiplied by 100. The experimental yield is something that always be stated. It's going to be expressed in the written problem, so just look for the problem. You'll find somewhere it's going to say how much was produced, or how much was made. That is my experimental yield. Bear in mind, yield is another way of saying produced, create, formed. So when I use this word percent yield, really what I'm trying to say is percent made. What percent did I make in my experiment compared to what I should have made in theory? Theoretical yield is the result of a stoichiometry problem. So you're going to need some stoichiometry in order to solve for the theoretical yield. It will never actually be expressed for you. Only thing that's going to be expressed for you will be the experimental yield. Okay, and we'll be seeing this, and we'll practice this on the next slide. In this problem, I have 3.3 grams of magnesium oxide is produced by the reaction between 3 grams of magnesium and 15 liters of oxygen. Please determine the percent yield of MgO. Alright guys, the first thing I think we need to do is label the reaction. The reaction is listed right down here and it's balanced. Let's go ahead and label it. The first number we see is 3.3 grams of something. That's 3.3 grams of magnesium oxide. Let's take a second and write this down. 3.3 grams. Now that is what is produced. Okay, that is what is produced in my experiment. It comes by the reaction of 3 grams of magnesium and also 15 liters of oxygen. Alright dudes, we're all set to go here. The goal is to try to find out what is my percent yield, meaning how much did I make compared to what I was supposed to make. And I've already told you actually, 3.3 grams of magnesium oxide is produced. This 3.3 grams actually is my experimental yield. That is what was produced in lab. What you need to now find out is what is my theoretical yield. What is my theoretical yield of magnesium oxide? Okay, 3.3 grams of magnesium oxide was made in lab. Now tell me, theoretical yield says, how much magnesium oxide should I have made? You have to go by it this way. You're going to take your given, which is 3 grams of magnesium, and do a stoichiometry problem that takes you to blank grams of magnesium oxide. And you're also going to do another stoichiometry problem that takes you from oxygen also to magnesium oxide. And so what you end up having is the same thing as a limiting reactant problem. We first have to find out which one of these reactants will run out first, and which one of these reactants, when they run out, how much magnesium oxide should they have produced. So our game plan is going to be simple. First thing, find out which one of these is the limiting reactant. Once we find that out, use the information of how much MgO I have to substitute that down into our problem right down here. And then my third step is going to be to solve for the percent yield problem. Okay, so I'm going to write my givens out now. My given is 3.0 grams of magnesium. And I'm going to just start it off with 1 mole of magnesium, and it's going to be 24.3 grams of magnesium. And this problem will be taken out, and I'm going to finish it because I want to find out how many grams, in theory, what's my theoretical yield, how many grams of magnesium oxide should I have made? Okay, and likewise, grams of magnesium oxide is going to go there, and this is going to be 40.3 grams from the periodic table, and this is going to be 1 mole of MgO. From the balanced equation, I say I have 2 magnesiums, so it's going to be 2 moles of magnesium per every 2 moles of magnesium oxide. Okay, so let's take a step back here. What do we got? If I use up all of my 3 grams of magnesium, the question is, how many grams of magnesium oxide should I produce? Let's take a pause and calculate. Okay, when all is said and done, what I've calculated out here is 4.97 grams of magnesium oxide should be produced if I use up all of my magnesium. Okay, so technically right now, I have the potential of making 5 grams of magnesium oxide. That's what I have the potential of. Now, just a little refresher, because I kind of went a little fast before. This number came from the periodic table. You look up magnesium, and atomic mass is 24.3. And likewise, magnesium oxide is a combination of magnesium plus oxygen on the periodic table, giving us 40.3. Now, the second half of the equation is going to go like this. I'm going to take my other given. The other given is 15 liters of oxygen. And I want to find out how many grams of magnesium oxide I can make with my magnesium oxide, with my oxygen. And let's bring this all the way out to grams of magnesium oxide. Because that's the unit is grams of magnesium oxide, I'll put grams of MgO as my last unit that's not canceled out. And it weighs 40.3 on the periodic table per 1 mole. Okay, let's begin the problem here. In order to use up all of my 15 liters of oxygen, we need to convert it into magnesium oxide. First step in the conversion factor is going to be 1 mole of O2 for every 22.4 liters of O2. Alright, now we need to cancel out moles of oxygen. We'll have moles of oxygen on the bottom. And there is a coefficient right here of 1. So I have 1 mole of O2. And on the top, we're going to magnesium oxide. And there's 2 moles of MgO. And I got that right from here. In every 1 mole of O2. Alright guys, let's press pause and let's calculate. Okay, when all is said and done, the correct number of significant figures, I find that I have 54 grams of magnesium oxide is going to be produced if I use 15 liters of oxygen. Now we're going to compare this. The two theoretical yields that I have here is that I could either have 4.97 grams of magnesium oxide produced by my magnesium or 53 grams. What I have here in my reaction is I have the potential of producing 54 grams of magnesium oxide, and I can get that if I use up all of my 15 liters of oxygen. Great. If I use up all of my magnesium, my 3 grams of magnesium, I have the possibility of producing 4.97 or roughly 5 grams of magnesium oxide. Whichever one of these numbers, 54 or 5.0, is the lower number I'm going to use. Okay, so right now I have a limiting reactant, and the limiting reactant is going to be magnesium can only produce 5 grams of MgO, so now this becomes my theoretical yield. That becomes my theoretical value of MgO that I could possibly produce. Okay, so magnesium becomes my limiting reactant. Oxygen, I'm going to have excessive amounts. It has the ability to produce a lot of magnesium oxide. I'm not even going to get close to that. On the next slide, what we're going to do now is substitute our theoretical yield of magnesium oxide into the percent yield equation. So my theoretical yield is going to be, let's go back one slide, 5.0 grams of magnesium oxide. So my theoretical yield, based on my stoichiometry problem, was 5.0 grams of magnesium oxide. My problem tells me that in the lab, I have 3.3 grams of magnesium oxide is produced. Now I'm going to use that number as my experimental yield. 3.3 grams of magnesium oxide was produced in my lab. I'm going to divide that and multiply by 100 to determine what is my percent. And what I end up with is going to be a 66% yield. And what I end up with is a 66% yield. So if I go back to my original slide, and I look at this, and originally I produced 3.3 grams of magnesium oxide. The whole question was, what is that percent yield? What is that as a percentage of what I should have produced? I should have produced 5 grams of magnesium oxide. The experiment only yielded 3.3 grams. So once again, the question was, what is my percent yield? It is what I made in the lab divided by what I should have made based on my stoichiometry problem. Turns out I made 66% of what I should have made. Alright guys, that finishes up our percent yield problem. Hope it helps. Have a good day.